everyone officially to the Hardware Acceleration Working Group, or HAWG for essentially short. This working group aims to drive the creation, maintenance, and testing of acceleration kernels on top of open standards, particularly C++ and OpenCL, for optimized ROS2 and Gazebo interactions over different compute substrates. This includes, of course, FPGAs, but also GPUs. The minutes of this meeting will be posted. Actually, you are seeing them right now in the screen. Let me get this link into the chat. There you go. So, so anyhow, feel free to send comments while or afterwards. They'll be out there. So before we dive deeply into the acceleration topics prepared for today and the agenda items, I wanted to go around the table and hear a bit about everyone willing to participate and give you a chance to quickly introduce yourself and tell us what you're working on or what you intend to do with acceleration. Since I'm at it, I'll just kick it off myself. Hi, I'm Victor. I work at Xilinx as a system architect, specialized in robotics. Got about a decade of experience in ROS and ROS2 and have contributed to some of the major stacks. I'm experienced with real-time, safety, and security. And over the past few months, I've been accumulating experience with HLS and OpenCL. As for what I'm working on, besides helping Xilinx with clients, my main effort concentrates on facilitating an open architecture for hardware acceleration in ROS. All right, so let me, since we are quite a few, let me start with from the top. Okay, Giulio, can you quickly introduce yourself?
Yeah, I'm Giulio Corradi. I'm the principal architect in the industrial vision and healthcare group.
Thank you, Giulio. Douglas Bertel.
Sorry, are you listening?
We can listen to you. Yep.
Yes. I'm a professor from Brazil, from State University of Santa Catarina, and I'm interested on hardware acceleration for ROS.
Awesome. Thank you, Douglas. G. Grigor.
Hi, yes, can you hear me?
We can.
Yes, I'm Gordon Gregor. I'm from NVIDIA, and we work on robotics, and we're interested in this specifically because we're looking to provide hardware acceleration or efficient hardware acceleration in ROS.
Awesome. Thank you. Amit?
Hi, I'm also with NVIDIA. I work with Gordon, responsible for product management for our autonomous machines products.
Awesome. Thank you, Amit. Chetan?
Sure. My name is Chetan Kona. I'm part of Victor's team in the Industrial Vision Healthcare and Sciences group at Xilinx.
Cool. Dimitri, and apologies, Dimitri, I don't think I can pronounce your last name. I think there's only one Dimitri in the call.
That's fine, thanks. I am from Ericsson Research, and I work with embedded system design and efficient hardware acceleration. This is my first meeting in this community, so I'll just listen in.
Awesome.
And yeah, look forward. Thanks.
Thanks to you. Thank you for sharing. Great. Gianluca?
Yeah, sure. Hello, everyone. I'm Gianluca Cagliazza. I am a postdoctoral research at Ca' Foscari University, and my expertise is in security. So I've been working on cybersecurity for robotic application for a while, and I'm interested in hardware acceleration also for security applications. That's why I'm here.
Cool. Good to have you here, Gianluca. Guglielmo?
Hi, my name is Guglielmo. I'm principal scientist from Macarena Labs for robotic and ML application on FPGA.
Thank you. Hemal?
Hi, I'm Hemal Shah. I'm from NVIDIA as well. I work with Gordon and Amit, and I lead up the robotic solutions engineering team here, and very excited about hardware acceleration for robotics.
Cool. Thank you. Okay, Kapitanuk.
Yes, hi everyone.
Yeah, there.
I'm Yuri. Yes, I'm a senior innovation engineer at Fugro, the Netherlands. So we are developing some remote and autonomous systems for maritime industry. It's unmanned surface vessels and remote operated underwater vehicles. And part of our systems already built it around ROS2. And I'm really wondering, because we need to go more towards autonomy. I'm looking for all these kind of like options, how to switch computational burden from the cloud infrastructure towards local computation. So that's why I'm just interested to hear and participate in the discussion. Thank you.
Awesome, awesome. This is definitely your group then. Cool.
Yeah.
Okay, Jasvinder.
Hi everyone, this is Jasvinder, working with Xilinx as a subject matter expert for graphics rendering acceleration particularly. But recently I have been working in various interesting projects like benchmarking of neural network performance on FPGAs and GPUs, and also accelerating computer vision functions on FPGAs. I'm new to ROS community, but really excited to be part of this group and looking forward to contribute to the best of my knowledge. Thank you all and nice to connect.
Cool, thank you, Jasvinder. Jorge Lamperez.
Hi, my name is Jorge. Thank you, everyone. I've been working with FPGA since I finished my master's degree. I'm independent. I would like to learn a lot in this group. This is not my full-time job. This, for me, is like a hobby. So I think that is a good proposal, and thank you for everything.
Good to have you here, Jorge, and welcome. KB?
Thank you, Victor. My name is KV Tanjavur Bhaskar. I'm AI and IIT Solutions Architect with Xilinx, also new to the ROS community, so very interested to learn more. Thank you.
Thank you. Maria Merlan?
Hi, everyone. My name is Maria Merlan. I'm a PhD engineer specialized in physics and telecom. I've been working in electronics product management for a while. I'm quite new in ROS. I joined recently Proxima, the company behind MicroROS. So for me, this group can be very insightful also. So thank you.
Super. And thank you so much for joining, Maria. Looking forward to cooperate with you from the embedded working group. Great. Okay. Matthias Kilat.
Hi, I'm from Apex AI. I'm a software developer there. We are a company that mainly specializes in automotive solutions based on some kind of ROS version, you could say. And we are providing also some kind of, we integrate zero copy middleware in this. That's where I'm currently working on. And we think about, adding hardware acceleration support to our data or messaging framework, and that's why I'm here. And I'm also interested in general high performance computing with machine learning applications, computer vision, and stuff like this. So essentially, what you needed those kind of computational power for. So,
thank you so much, Matthias. Awesome. Michael Sapke.
Hello, I'm Michael or Michael. I'm calling in from Germany. I'm industrial lead also at Xilinx and work together with Victor.
Thank you so much. Murali?
I'm Murali Gopalakrishna. I am from NVIDIA. I had the robotics program here.
Great to have you. Thank you. Nicolas Mal?
Yeah, hello, I'm Nikolai. I'm a PhD student at the University of Southern Denmark, and I work on a project called Drones for Safety. And we're quite interested in hardware acceleration, both for ROS and ROS2, but also in general for AI and stuff because of the constraints of onboard compute on a drone. Yep.
Awesome. Thank you so much. Pedro?
Hi, I'm Pedro. I'm from Argentina. I am a professor at Buenos Aires University, and I also work with our robotics group. I also teach digital systems with FPGAs. So this group is very interesting for me to teach to my students.
Awesome. Thank you so much. Randy?
Yeah, hi, this is Randy Hartgrove. I'm on the apps team at Xilinx, and I'm just curious to see what this is all about and interested to join the discussion.
Awesome. Okay, Robert Wilbrandt.
Hey, my name is Robert Wilbrandt, and I'm just a computer science student, generally interested in different kind of hardware acceleration, so I just decided to listen in.
Cool, thank you for joining. Raffin?
Hey, I'm a computer science PhD calling in from Southern California, a longtime ROS contributor. I work on cybersecurity for robotics, but I'm looking forward to kind of get back into my roots with a lot of computer vision and machine learning.
Awesome, awesome. Thank you, Raffin. Said?
Hello, everybody. My name is Said Zarai. I am head of innovation at ABB Robotics. And obviously, we are interested in any kind of new technology that can help us take steps forward.
Thank you so much, Said. All right, we're reaching the Sam.
Yeah, hello, my name is Sam Mitchell. I'm from the Automotive and Rail Innovation Center from Germany. And we are mainly developing positioning solutions in sensor fusion with ROS. And I'm looking forward to hear some more about hardware acceleration for visual odometry.
Cool, cool, cool. Welcome. Thomas?
Yes, hello everybody. My name is Thomas Thoresen. I'm with Xilinx. I just recently started working on the ROS2 stack together with Victor.
Cool, thank you. And finally, as per my list, but if not to speak out, Vishal. We can't hear you, Vishal, but maybe we'll hear you.
Vishal put a comment in the chat.
Okay. Is there anyone who I left and I missed? Doesn't look like. All right, so on the interest of time, then I'll close this introduction section and we'll dive directly into the second point in the agenda. So let's dive a bit into the objectives and rationale. Essentially, the first topic, or this topic itself, relates to probably the fact that, as most of you know already, there's a critical relationship between the hardware and the software capabilities in a robot. ROS computational graphs need to be mapped appropriately to hardware. And that's where the data layer graphs comes in and why it's relevant. Robotic systems usually have limited onboard resources, which difficult system integration process. And this is particularly impactful when extending, adapting, or fixing actual robots, making it really hard to meet real-time requirements and limiting robot reaction, speed, or capabilities overall. It's thereby, in our opinion, essential to choose a proper compute platform for the robotic system, one that simplifies system integration, meets power restrictions, and adapts to the changing demands of the robot. Now, the hardware acceleration working group will focus on reducing the time, that is, real fast as opposed to real time, to compute gazebo and ROS2-based robotic flows by producing specialized compute architectures that rely on FPGAs and GPUs. Alignment with various other groups is expected to happen and will happen in the future. Now, let me share my screen at this point again. There we go. And dive a bit more into the objectives. So hopefully you can see it right now. Can you see my screen?
No, now we can see it.
Okay, you can see it now. Great. As I was saying, the objectives essentially in the community repository of the ROS Acceleration Organization reflect the short-term goals that we've set ourselves, but of course this is open to input and contribution from third parties. Our focus essentially will first be on tools to facilitate acceleration flows. Then we will aim to provide reference examples. And after that, we'll facilitate benchmarking utilities, which will be critical to establish compute baselines when comparing or evaluating acceleration. And this is extremely important, especially the benchmarking part. And we'll share more about this in future meetings about what's the methodology we have at Xilinx. And we definitely encourage you to use when it comes to acceleration. Now, after that, we'll survey the community to capture additional interest of what people actually demand in terms of acceleration. And finally, we'll produce demonstrations with real robots. Now, to steer the development of this working group, we have selected this reference hardware platform. This is what I'm using and what most of us are using on our daily basis for development. Essentially, we are using the K26 adaptive system on module through the Kria KV260 kit. And this is described in the repo. Having a well-defined reference hardware platform is key to ensure reproducibility and good user experience as well as performance in the beginnings of this group. And this will hopefully empower many of you to reproduce the work, to make contributions and make your own accelerators for whatever your use case is. Of course, having one official reference hardware platform doesn't mean we can have more in the future. And this is actually at the very core of our architecture. I'm personally extremely excited about this because, again, we designed this architecture with this in mind. And that's pretty much something we'll discuss into, I think it's the fourth or the fifth topic in the agenda. We'll talk about this more later on. Now, let me dive.
Maybe, Victor, it'd be good at some point to discuss how we could add reference platforms, because it would be a good test of that the system is open and scalable if we have other hardware platforms we can use as well. Absolutely.
I'll essentially explain more about that when we reach the fourth item in the agenda, looking at it right now, because there's already been a request from the community. So definitely count on that. All right, so speaking now about the architecture. So the architecture builds on top of three pillars. First, the ROS aim and build system. Second, the ROS meta build tools. And third, firmware particularly for whatever platform and accelerator we are using. Now, Colcon and AMENT extensions are pretty straightforward, and I will not be discussing them right here in this meeting, though of course reach out and ask questions if you need to. The firmware helps make the architecture platform agnostic, serving for essentially extending this to not just embedded edge boards, but also to PCIe cards, to data center technologies for acceleration, as well as cloud acceleration. As pointed out before, in the objectives, we'll first focus on facilitating the tools and reference examples to later dive down into extensions. This is exactly what the initial architecture in the hardware acceleration working group objectives reflects, and what we will essentially be doing in the coming months. Now, the first contribution that you will see out there are concentrating on the ROS2 build system, that is AMENT. And fortunately, we did manage to get legal approval to share this, and you can see this right now over here. So this has been disclosed, and you can review it yourselves. So these are the extensions we propose for essentially the AMENT ROS2 build system to integrate some of the capabilities for hardware acceleration. So happy to receive your input on that. Now, let's dive into an actual walkthrough on what this is from a code perspective, real quick, given the time we have. So right here, you can see the AMENT-VITES source code. These are just simple series of macros which extend the ROS2 build system to include, in this case, the VITES unified software platform. In a nutshell, what this CMake logic adds is the capability to, within your cmakelist.txt files on each one of your ROS packages, to literally, by just adding this block, by just using this macro and adding this block, defining on your packages kernels directly. So it's that easy. The rest happens automatically if the structure is kept. That's why we put so much effort into ensuring that this architecture is consistent. Now, within the macros, you can define the name of the accelerator, the source code involved with it, the corresponding platform and technology, its targeting, headers, and finally, the build targets. We are initially proposing 3 different build targets. These build targets are the ones that come from our VITES technology. And without getting into too many details for the sake of time, we do provide 2 build targets for emulation. One where you can simulate the programmable logic, the FPGA, and you simulate it within an emulation. So it's a simulation within an emulation. Second one, where you can emulate the programmable logic, the FPGA, again, also within a QEMU emulation. And third and last but not least is, of course, the typical hardware targets to run it in your boards. Now, the importance of these first two was discussed in one of the threads of this course, and essentially connects to the fact that typically building hardware accelerators takes a bit of time, depending on the complexity of your accelerator. So with these first two, you can accelerate literally your development significantly because it takes much less time. And it helps you keep up closer to the typical software development flow you probably will have in your workstations. Now, this is all it's needed. Let's now look at an example of what source code looks like. This is a publisher, just a simple publisher that is trying to publish at 10 Hertz. That's what this wall rate is here for. The result of a vector add operation. We are on every iteration of this loop, randomizing these vectors and then adding them in this function. Now, this function looks like this. It's a silly function that has been purposely made computationally expensive to illustrate this, this acceleration silly example. So as you can see, it's just adding the vectors. That's pretty much it. Nothing much more complex. Now, what we will see is that due to this computationally expensive function, we will not be able to essentially meet the objective of publishing at 10 Hertz. So that's where acceleration triggers, that's where it comes in, and that's where we propose this second example. And again, we're working really hard at Xilinx to disclose this ASAP. It's right now in legal, and it'll get to your hands as soon as we can. And again, this is just the same publisher using the same ROS logic. You can see here that we are instantiating the node, creating the wall rate. And then here we are initializing the environment for OpenCL. So we are using OpenCL here to, as pointed out, C++ and OpenCL are the core baselines of this working group. And that's what we will be focusing on. So besides that, we are creating the buffers to map memory between the programmable logic and the PS. And then we're getting into the main loop where all we are doing is exactly the same. We are randomizing the vectors, we're passing the arguments, and just adding the kernel, calling the kernel. So let's look at this directly into, so before I show it to you in a running board, let me show you how easy it is actually to invoke this. So here you can see the typical Qualcomm build. You mostly are using yourselves, and now these two arguments are meant to separate the resulting folders from the workstation builds to the embedded ones. And everything you need to do, really, I mean, these are optional. You can do it or you don't have to do it if you don't want to, but this is where the real magic happens. These mixins, which are generated automatically out of the firmware provided for each one of the particular boards and tie and connect directly to the AMENT and Qualcomm extensions, is everything you need to do. By just passing this flag, Qualcomm is automatically going to reconfigure itself to know it needs to build for the embedded platform in the mixing, that is cross-compiling. It also knows which platform for acceleration it should select. And it also knows essentially what type of accelerators it needs to generate, because it's going to look into the corresponding CMake files with the macros that I just showed before. So in this case, we're just essentially building a very, very silly vector publisher example. But we can see how essentially, so it did cross-compile. In this case, we don't have any acceleration whatsoever because this one doesn't include it. But if we look into the accelerated version, for example, we'll see how it has also generated, in this case, a software emulation target that I did before. But we'll see it now in the real hardware. So again, pretty straightforward, very easy, and it only needs you to literally select which parts of your code you want to push into the hardware, you want to push into an FPGA or to a GPU as well in the future. Now, to the examples, I'm going to run first the vector add publisher. And as promised, you can expect it not to meet the corresponding target in terms of publication rate. Now, of course, in industrial applications, our advice would be for you to instrument your source code using proper, essentially, instrumentation tools such as LTTNG, and out of that, get your baselines and benchmark information. Of course, for this silly example, we can just use the ROS2 CLI tooling, which is what we are doing right here. And we can see that it's publishing at 2 Hertz. So about 5 times below what we were aiming for. Now, let me stop this and let me launch now the accelerated version. And you will see how essentially it's loading the kernel. And we will now do exactly the same one, subscribing to a topic where the accelerated version is publishing. And you can see how from 2 Hertz, we jumped directly into more than 3 times above. Now, the beauty of this is that if we look back at the changes we made in the source code, they were these 3. And I say beauty because really we haven't fully optimized this function. The actual changes we've made with this pragmas are just selecting actually which ports are used within the RTL model that gets created. To give you a bit of additional insight, the HLS interface specifies how RTL ports are created from the function definition during the interface synthesis. Now, sharing ports, which is what happens by default with HLS, means essentially you save FPGA resources by eliminating AXI interfaces, but this also limits the performance. So essentially, the MAXI port allows for independent read and write, but in this case, we want to read simultaneously from 2 different vectors. And so what we do essentially in this case is create different bundles. We separate the different bundles, creating 2 AXI interfaces and obtaining the boost we just saw. There's no further optimization in this particular piece of code. There's no loop unrolling or pipelining, nothing of that. And all those will lead to further essentially upgrades into the kernel itself. Now, these examples give you a quick intuition of how easy it is now to use hardware acceleration in ROS with Xilinx's tools. And technically what we've done is integrate the VITES unified software platform in ROS as a first-class participant. Now, let me dive directly into the 4th topic of the agenda, which I think it was requested as well, which is how do we extend this to other boards, right? And that's something we paid lots of attention, as we said, not just because it was requested, but at the very beginning, because we ourselves use different boards for our development. You can see here listed some unofficially listed boards, because again, in our team, there are many other people using it, and we definitely want to open up the door for this to happen. Now, there's a section here in the community repository which says adding your board, and this should satisfy most of your needs. We're working on this right now. In a nutshell, this will be translated to a series of artifacts that you need to place into a repository. This repository will fit into the 3rd pillar. I explained, the firmware pillar. So just by having that repository into your workspace, you are pretty much done. The rest of the logic is done by our architecture. And of course, we're working right now to try to translate this into a series of instructions. It's essentially taking a bit for 2 reasons. First, because of internal processes in Xilinx, and second, because we want to coordinate this also with Open Robotics. So that essentially we don't go crazy, we start getting forks of forks, and we go, well, crazy before even we got started. So we are trying to formalize this as part of a formal ROS enhancement proposal. So if you want to help with this, reach out to me. Now is a great moment. We're doing this. Nevertheless, for Pedro's request on the Ultra 96 version 2, you definitely can count on our support and help. And as I said, the instructions will be pushed to the community repo ASAP as soon as we are ready. Pedro, you raised this topic, so I wanted to open the mic to you real quick if you want to add something. Did I cover your request?
Yes. I'm interested to the Ultra 96 because it's a popular board, and I know most of us have it. And by the way, there is about 12 weeks of delay for the Vision Starter Kit. So I think if we use the Ultra 96, we can start working with real hardware. So that's my
Awesome.
principal interest.
Yeah. No, you're right, and apologies for the delay. I mean, too many people is trying to buy too much from us. I guess that's good news. But anyhow, the popularity is well deserved. I can absolutely assure you that. But yeah, apologies for that. And the request is very well understood, Pedro. So definitely count on my help for doing that. Now we reached the top of the half an hour, but I wanted to open up for Q&A. So whoever needs to jump out, feel free to do so. Thank you so much for showing up. Those of you that want to stay and ask questions, I'll stick around for a bit more. And yeah, opening up the Q&A section.
May I speak?
Please, go ahead.
It's I didn't check the repositories, but it's something like a getting started guide, so we can start playing with the repository of the new things that you uploaded.
So at this point, Pedro, I don't think we have contributed with an open, with kind of like a 101 or getting started guide. This is a good suggestion, and we'll note it down. And definitely doable. I think the best way to formalize this is to probably create an examples repository where each one of the code examples is documented with its corresponding README. This, if done appropriately, can also facilitate kind of like continuous integration on our side so that we know things essentially are working, and when they break, we can just jump there and fix it. But no, noted, and thank you.
Okay.
I have a question.
Please.
What would be required in terms of ROS, for example, to use it? Is it running with the current ROS rolling, ROS Galactic, or something earlier?
So right now we are developing on top of Foxy.
Oh, Foxy. Okay.
So that is pretty much the assumption we've made internally in Xilinx. Now, it doesn't mean it won't work into other distributions. However, right now, all of the packages need to be built from source. We haven't pushed this into the build farm. We definitely have the intention to do so, but again, step by step. So right now, I would say, Matthias, I believe that you're free to just fork, clone this repository, and try with pretty much newer, I would say, new ROS versions, including rolling, should be good to go. I don't see why this should collide.
Probably we'll try in the next month or something, because I'm kind of busy, but it would be cool to try. Because I'm asking because our working assumptions, or in our company, for example, is shifted towards the ROS Galactic essentially, or something later. Mm-hmm. Would be cool if if it will work with this. Thanks.
I mean, I can just say that's good information. And if you have a good use case and a strong use case for us, then reach us out, let us know, and we'll consider jumping into Galactic. I'm not pushy towards one or the other. I just think Foxy is the LTS, and so that's why we stick with it.
Yeah, sure. We are just exploring also, so no strong use case, but yes.
Okay, thank you.
Hey, Victor, as a question, this looks like it's a great way to provide acceleration. Is this within a single ROS node, or is this providing acceleration across different nodes that are performing different functions?
So to give you a short answer, this is node agnostic, meaning we give the flexibility to the architect to pick exactly how they want to structure their acceleration, meaning they can literally do it in different ways. Now, of course, this comes at the cost of having to also use OpenCL. We could literally, and if this is a request, then I'd like to hear it, but we could directly kind of like template how the acceleration is going to be shipped. And literally by using templates, we could remove much of the hurdles of using certain OpenCL aspects and literally just make it even simpler for people. But this would, of course, put boundaries on what type of accelerators users will end up being producing. Now, we reviewed literature quite extensively, I'd say, and most of the past approaches, which are impressive and awesome, tend to make like design choices on this direction. We would prefer at this stage not to make them. And that's also what we would encourage, both across FPGAs and GPUs, because again, every use case in robotics is different. And potentially we want that choice to be made by the architect, not ourselves now while designing the tools. So that's the current status, but I'd be frankly very interested to hear if you've got different thoughts or different ideas.
Yeah, maybe to share from an NVIDIA perspective. So what I'm particularly interested in is accelerating an execution graph. So I'm interested in finding ways to not accelerate a single node, but a graph of nodes that are performing functions that are needed for robotics. And a good example of that would be most robots need to have some perception pipeline that has to be performed. And each of the individual nodes today have a lot of, in ROS2, there's a lot of fixes to superfluous memory copies. So data can be moved as long as we are within the same processor thread without having a cost. But that isn't designed well for hardware acceleration. So we're really looking for a way to split up computation across multiple nodes in a way that makes sense from a functional perspective, but allow that such that we can use hardware acceleration in those nodes across that execution graph.
So that's interesting, and I like to hear that a lot, because that's kind of like, I pointed some of the NVIDIA folks in the past towards that direction. And essentially, this is very important. We get it right from the very beginning. The actual impact of acceleration is going to happen at two levels. First, at the application level, by showing stuff like what I showed today, just a simple publisher accelerated. The second one is accelerating the computational graph. And that's what you have just described. Now, accelerating the computational graph requires you first to accelerate or optimize the underlayers, the ROS2 underlayers. That means going from the link layer up to layer 7 of the OSI stack, considering DDS, and then behind that, the networking stack, and so on and so forth. That is something that goes beyond one single company, and that's where I'm hoping that cooperation happens. And this is something that many roboticists don't quite grasp today. They just believe that if they accelerate the end application, then that's pretty much it. And that's not the case, because there are middlewares, and the bottlenecks in many cases is below ROS. So impacting that will eventually lead to accelerating computational graphs. And I'm very happy to hear that coming from you. So looking forward, probably we can discuss this a bit more offline. I'd love to hear a bit what's the direction you guys are planning and how we can push together. But awesome, great to hear.
And to maybe give a concrete example, right? I can imagine that on one of your FPGAs, maybe somebody implements a visual odometry function, and before you can run the visual odometry function, you need to do some image processing. So you have one node that wants to do image processing and another node that's doing visual odometry. And if I were Xilinx, I would want to not have to copy memory out of my FPGA when I'm done with color space conversion and then copy it back into my FPGA to run visual odometry. It would be nice if there was some way to actually be more efficient around for the movement of that data between those nodes.
Definitely. Awesome, thank you. Okay, more questions, comments?
Just expanding maybe on this a bit. We are in the process, it's an early prototype of adding something like you said, but not for accelerators, but we began to add our zero copy middleware, which essentially avoids, under certain circumstances, unnecessary copies in the under layers of ROS. But the key question, of course, for you is then how to make this also work for accelerators. And this I cannot answer, this I do not know, but that's why I'm essentially here to maybe get some ideas or explore this.
Well said, yes. And just to clarify, you're speaking about your work, the Apex AI work on iSeries, right?
Yes, that's an I would call it an early prototype that the integration that is not the iSeries system itself, but the iSeries system itself operates on POSIX shared memory and is not able to interface with accelerators as of now. Would be cool if it would be in the future, and maybe this is possible, maybe not. Cannot.
No, I think definitely, and technically it's viable. We just need to find time and motivation to work on it. But definitely leveraging the capabilities iSeries promises. I haven't tested it myself, but I read the documentation. The microsecond level interactions, the intra and inter-process is definitely something we do want and we should consider. I think we shouldn't though stay at that stage. At least from Xilinx's perspective, we're looking at this holistically, meaning we want to accelerate interactions between nodes in a computational graph using inter-process, intra-process, and also intra-network, because many robots actually do work in a full distributed way. Think about fleets, or even think about just one robot with distributed components communicating over different networks. So, so definitely we'll get back to that, Matthias, and thank you so much for raising. Good. Okay, so I would.
Hi, Victor. One thing, I would like to know if you have run this example that you explained in a board, in a hardware board.
Yeah, you just saw it running in hardware. The ones that I showed were running on hardware.
Oh, okay. So, but it's not the CREA board, no?
We're running in different boards. So we have the CCU 102, the KB260, and the CCU 104. Any of those should run right away today. The others, it's going to take a bit more of an effort from our side, but we'll get there.
Okay, and you are using Petalinux for creating the software, or you are using a Ubuntu-based software?
So the current prototype that I showed is based on Petalinux, which is Yocto Open Embedded, for those of you not so familiar with it. But definitely we're looking forward, Jorge, tackling your question. We're looking forward to also consider other file systems beyond essentially these embedded file systems based on Petalinux. So so if you're interested on this, I think you'll have tools in the future.
Okay, another thing, I've been dealing a little bit with the starter kit, with the applications, with the smart cam, NLP, and all of these things. I've seen that they are using a platform for each of the applications. I would like to know if for robotics and for this application that you have shown us, if you are using a special platform for BTs, or you are using one that is in the starter kit?
So short answer, because we really are out of time and it's a bit late here in Spain. Short answer is the platform is defined by the mixing you pass on the Qualcomm build argument. So essentially, the platform is defined by the firmware repository you have in your workspace. Now, as for the actual platforms that are used in the different accelerators in the vision kit of KB260, that's beyond this discussion. But what we are doing is using one particularly tied for the robotics use cases. So that one, anyhow, will be included within the firmware repository we're working to disclose. So you'll have everything you need. And with that, I'm going to thank everyone once again for this extra 15 minutes as well. I think it's surprising. I managed to get so many people until 15 minutes past the time. So thank you. Looking forward to hear your thoughts about this first disclosure. Looking forward to discuss with some of you offline some of the ideas. And to wrap it up, I would encourage you all to review the source code we have disclosed. I mean, invite this in the ROS acceleration organization to show up in the next meeting, where we'll be providing a deeper dive into more source code examples and optimize the example we started showing today. And to all those of you who are actually working right now with the board and asking questions related to it, if you have cool use cases and are interested to know more, I would say reach out to me or any of my colleagues privately. We'll study the opportunity of giving you access to our early access launch, where you will find information ahead of these meetings. And with that, once again, thank you all, and we'll see each other in the next meeting if you decide to come. Thank you and have a great one. Bye-bye.
Right. Thanks a lot.
Thank you, Victor.
Thank you
very much.
Right.
Thanks, Victor.
Bye.
Bye. Thank you. Bye-bye.
Bye.